Let's do this. Magic pen. So in the study session on Friday, I put the recording up on my playlist. I picked a problem out of the book because I didn't know how to do it when I first looked at it. And I've done enough calculus in my life that often I can just look at a problem and say, oh, I know how to do that. And I don't bother. But this one I looked at and I was like, oh, I don't know how to do it. And I tried 3 times, so 4 times, and failed each time. So I'm going to present this problem again. My failures are on the video if you want to go watch those. It's about 10 minutes of failure. You might ask yourself, oh my gosh, this is the teacher that can't do math, right? But something to consider is more than half the math I've done in my life, I've done wrong first before I get it right. And everything, almost everything you see in class is a rehearsal. I've already done it. It's a play. I make it look easy, right? But the bottom line is it's not. So the problem from class was, or the study session Friday, was the integral of the square root of x minus 1 over x to the 5th with respect to x. And in class, in the study session, I tried various algebraic manipulations of that. I tried a few different U substitutions, and every one of them made it worse and left me stuck. And one problem that came up is you can separate a root on division if both pieces of the division are positive. But is x minus 1 always positive? And no, for some x values it's negative. Is x to the 5th always positive? No, it can be positive or negative. It depends on x, right? So separating the division is a problem. And then it hit me, oh, I could just rewrite this sucker. Switch. And I'm going to ditch the integral for a minute and just focus on the integrand here and say, what if I wrote it as x minus 1 over x times 1 over x to the 4th? If I pull out an even power, I don't have to worry about positives and negatives, right? Because if the power is even, the square or 4th power of a negative number is always positive. So the square root of this right here, I can separate on the multiplication there. What's the square root of 1 over x to the 4th? 1 over x to the 2nd, so this becomes 1 over x to the 2nd. Now, normally, when you take the square root of some squared thing, you have to worry about absolute value of it, right? Because the definition, square root of x squared is really equal to the absolute value of x, not x. But do I have to worry about that with a square? No, it's always positive, or at least not negative, right? So this gave me hope, and so I continued along this path. So I'm still stuck with the square root here of x minus 1 over x. And then when you see x over x like that, don't you just love canceling it? Right? But the negative, I do. I love canceling stuff. It just totally makes my day. But the negative is standing in the way of that. So I have to rewrite that inside there. So I still got the 1 over x squared hanging out. And inside, I can say, well, that's just x over x minus 1 over x. Now that I've separated the numerator, I can cancel something and get some enormous satisfaction, even if I'm not done yet. Okay? So there's little things along the way. So now I have 1 over x squared times the square root of 1 minus 1 over x. And does anybody remember what the derivative of 1 over x is? What is it? Not ringing a bell? No, that would be the integral. Yeah, so the antiderivative, but the derivative 1 over x. So just new page, right? If I take the derivative with respect to x of 1 over x, which could be written as x to the negative 1, well, that's going to be negative 1 times x to the negative 2, which is really just negative 1 over x squared. Oh, I've got one of those in my problem, right? Excitement, right? So that says, oh yeah. So I saw, as soon as I saw the 1 over x and the 1 over x squared, I'm like, boom, I got a u. So my candidate for u then, and usually with the u, you want to take as much as possible, but not too much. It's a very fine line to walk. That right there is going to be our u. So let's try it. So if we squeeze down here, u equals 1 minus 1 over x, that implies that du, well, I love the derivative of 1, right? It's just 0. The derivative of 1 over x is negative 1 over x squared. Compounding with that negative there, what's left here? Just 1 over x squared, yeah. So this is 1 over x squared dx, which is just what I have outside of the square root. Okay, so I'm going to put this all together on another page just to summarize. And it only took me like 5 or 6 tries before I found the right substitution. Okay, so, and it's just, you know, it depends on the day. Do you see the right thing? So again, we started off with the integral of the square root of x minus 1 over x to the 5th dx. After a little bit of algebra, we were able to rewrite that as the integral of 1 over x squared times the square root of 1 minus 1 over x dx. Choosing u to be the new inside, we end up with a du that is exactly what is outside of the square root. Dx. So when I rewrite that integral there, it's now just the integral of the square root of u. Right? Because this whole inside is my u, and outside is my du. And that's no problem. Either you remember the square root or you change it to the 1/2 power. Anybody remember the derivative of the square root on its own? Or well, I guess we better write the power. I'm thinking I'm getting derivatives and integrals confused. When that happens to everybody. If I write it that way, I can say, oh yeah, add 1 to the power. That gives me a 3/2 and divide by the 3/2. So an antiderivative for the u stuff would then be 2/3 u to the 3/2. Because dividing by a fraction is the same as multiplying by its reciprocal. Since I don't have boundaries here, I have to tack on a plus c. And I probably should substitute back in my 1 minus 1 over x. So let's go back to black here. So it looks like 2/3 parentheses 1 minus 1 over x, close parentheses, to the power 3/2, and then plus c. Are there ways to algebraically rewrite that? Absolutely. Do we really care at this point? Not really. We have a reasonably good-looking antiderivative, don't we? It's pretty good looking, isn't it, Clint? What should we do next? Take its derivative and see if it gets us back where we started. Yeah, so on any of these, like if this was an exam and I had time, that would be my next step. I would take the derivative of this right here and hope I can get it to look like the blue thing or the black thing after I take its derivative. That's what I would do next. I'm going to skip that step and move on, but again, whenever you can spare the time when you're doing your homework, and again, I apologize for making the homework so long. It's an oversight. I will be more careful in the future. You don't have a check your answer button on the test, so before you hit check your answer, use something. Diving to some online program like domyderivativesforme.com or takethisintegralforme.org or Wolfram Alpha, that's not the best one because I'm probably not going to let you use those on the test. If I do, part of the test will be no technology and the other part of the test will be use whatever technology you want. Okay, so, all right, questions? Okay, let's try another one. I put a cute one in my notes this morning. Where did that page go? Here, right here. That is a cute one. All right, so here we're going to do a definite integral, so we're going to throw boundaries in there. And I want that sucker right there. Let's copy it It's so pretty. Okay. So let's see. Did I copy that right? Yeah. First thing I thought of when I saw this was double angle formulas from trig. Remember those? And those will become handy sometimes. Sometimes there is no substitution until you do some algebra. That algebra may be identities. So I started looking up trig identities, and everyone I plugged in made it worse. So I'm going to save you the worst stuff. And so I thought, okay, well, other thing I notice here is, well, the derivative of the sine is the cosine, and the derivative of the cosine is the sine. That's nice. My problem here is that I have a denominator. And so often a substitution happens related to the denominator. So after I tried several identities, I said, well, let's just try let the denominator be u and see what happens. So I, after a couple of failures, said, let's let u equal 4 minus the cosine of 2 theta. So what would du be then? Let's see, derivative of the cosine is negative sine. Derivative of 4 is 0. So I get 0 minus a negative. So I think I get what? The sine of 2 theta. What else? Times 2 because of the chain rule. Yeah, so we have the chain rule within the chain rule here. Because remember, substitution is just reversing a chain rule. Oh gosh, that's the numerator. Right? So here's my u, and here's my du. Now I'm going to ignore the boundaries for a moment. I talked about this in class the other day. Boundaries are dangerous when you switch variables. So I'm just going to say I have the integral here of 1 over u, right, du. Again, this denominator is my u, and this stuff up here is my du. Antiderivative of 1 over u. Natural log. Yeah, and technically, it's the natural log of the absolute value of u. And then since I don't have boundaries in my red stuff here, I'm going to put a plus c. But once I put the boundaries in, the c goes away. So, and again, whenever we do substitution, there's boundaries. Always don't go plugging in stuff right away. I always recommend reverse substituting. So substitute back in what u is. So related to the black integral here, I now have the natural log of the absolute value of 4 minus the cosine of 2 theta. And sometimes the absolute value is going to cause us grief, sometimes it won't. Here we're going to be okay. Now that I've put theta back in, I can say, all right, put the square brackets around the antiderivative, ignore the c, and whip out your calculator. Or, if you remember trig stuff in your head pretty well, I don't even think we need a calculator here. All right, so let's see. I need to evaluate this at pi over 2 for theta. 2 times pi over 2 is pi. Anybody remember the cosine of pi? What is it? -1, that is correct. So that's going to give me a 4 minus -1, which is 5 on a good day. So then I'm going to get a natural log of the absolute value of 5. 5's positive, so absolute value is not going to hurt anything. And then we have to minus when we plug in 0. What happens when we plug in 0? Cosine of 0 is 1. 4 minus 1 is 3. So it looks like I have the natural log of the absolute value of 3. Any other tricks I can throw at this? Simplifying logarithms. Log of a difference is the quotient of the logs of the argument. So this could also be stated as the natural log of 5/3. And since those are positive, I don't need to worry about absolute value. Now, since I have boundaries here, this would be a good time to say, hey, GeoGebra, what's going on? Does it really equal the natural log of 5/3? So let's check. Started GeoGebra yet. Wolfram Alpha is another cool one, but I will not allow that on certain parts of tests. I guess I should show it since I've mentioned it every day. Did I ever show it in class? I don't think so. I did show it one day? Okay. Yeah, all this technology is just amazing. When I was taking calculus, there was zero technology. My calculator could add, subtract, divide, do square roots. Couldn't quite graph yet. I think it was the next year that TI came out with one of the first graphing calculators. All right, so let's see. I want to take a look at, was it 2 times the sine of 2x divided by 4 minus the cosine of 2x. What I wanted, right? Okay. And then I was curious about that from 0 to pi over 2. So I'm going to graph x equals pi over 2. All right. So I'm going to get that chunk of area right there. Let's zoom in on it. Yeah, it looks like that's the intersection there. So we're going to get that area. And so in GeoGebra, I just say, okay, give me an integral with a function, start value, end value. Function here is called f. Start value is 0. End value is pi over 2. And it's automatically shading it, looking good. And then we hit enter, and we get 0.51. Let's see. Does GeoGebra know the natural log? LOG. Aha. LOG. Base is natural log E, right? And our x value is 5/3. And 0.51. Yep, GeoGebra says the area agrees with our calculation. Cool. Very nice. All right, Wolfram Alpha, just for fun. Wolfram Alpha. The trick with Wolfram Alpha is figuring out how to type it. And most mathematical, what's that? Yeah, parentheses help. They have some links here to try, they'll give you some example things. But most math software has similar commands. So if one program has a function called integral, another program will have a function called integral. So I'm going to try and type it like I did in GeoGebra. I'm going to type integral parentheses. Now here I have to type in the whole thing. So that was what, 2 times, no, yes. Sine of x, nope, 2x, right? And some computer algebra systems want you to put a times between the 2 and the x. Some don't care. My guess is this one doesn't care, but I'm not sure. Divided by parentheses 4 minus the cosine of 2x, close. And if I just hit enter, it'll try to find an antiderivative for me. Natural log of the cosine of 2x minus 4, which is pretty much what we had but flipped without the absolute value. Okay, so that's equivalent to what we had. I can also come in here and say, comma, start at 0, go to pi over 2, and hope it recognizes I want to evaluate it. And if I typed it right, it'll do it. If I didn't, it'll give me something bizarre. Ooh, didn't like that. That's some, see what I mean by bizarre? You blow that up. That's bizarre. Okay, so apparently I didn't type it right. Oh, I closed my parentheses in the wrong spot. That one. Parentheses, right, Darren? Ah, there we go. It did it. And in a lot of computer algebra systems, although in most math classes when we write log, we mean common log base 10. In most computer systems, log means natural log. Okay, not common log. So cool. Sometimes Wolfram Alpha can show you steps. Sometimes if you click that, they say, yeah, good, send us some money and we'll show you some steps. Like GoPro. They might have a trial version, I can't remember. But it's relatively inexpensive, but again, use your money wisely. I'm not sure I would buy that. My nephew was doing engineering for a while, and for Christmas I bought him a 1-year subscription, and he liked it. Okay, let's do another one. Where are my notes? All right, how about 5, 6, area between curves. Okay, so here's the problem I want to take a look at. We can use integrals to evaluate the area between curves. We've looked at that a little bit, so let's look at it a little bit more. That means I'm going to have a definite integral. So here the functions I want to consider are x squared minus 1 and 1 minus x squared. And when I put them together like that, I get this weird big parabolic football kind of shape. Right? And so I want to find the area inside, and whoa, that was cool, in between these two curves between -1 and 1. Okay, so that's our goal here. So to do that, I want to come up with a bunch of rectangles saying how tall. Right? And basically, I want to go from the bottom curve up to the top curve. Okay? So I just need to devise an integral that shows the heights of the things I'm doing here. So let's steal this image. It's kind of big. Can I shrink it down? Oh, you're beautiful. Thank you. Page. Screenshot that picture. We're going to need that. Okay. So I want to find the area here, and if you think again about sums, which is where an integral comes from, we've got a bunch of rectangles that we're going to span across here. And the height of any one of these rectangles, the red curve is g of x. That was my 1 minus x squared. The green curve is f of x. That was x squared minus 1. And so the height of any one of those rectangles, picking an x value in between, is going to be just the distance between the y value for g of x and the y value for f of x. And when you're finding area, you just integrate across the height for a given interval. So that means to find this particular area, I want to integrate from -1 to 1 f of x, which is, no, g of x first, which was what, 1 minus x squared. And now to get the height, I need to subtract the lower function, x squared minus 1, with respect to x. So that integral right there should find me this particular area. Some things to notice about this. Would you agree that we've got some symmetry going on here? So that this half of my area is identical to the other half. So what I could do to make things easier is just double the integral from 0 to 1. Because I love plugging in 0. Right? It's way more fun than plugging in -1. Well, it's easier at least. So that's what I'm going to do. I'm just going to make it easier. Notice these functions are evenly symmetric, and so that means I can just get by with doing half of the integral. So new page, let's do it. We want twice the integral from 0 to 1 of x squared. Nope, get that backwards again. Often I've made the mistake when I'm looking at two functions of stating them backwards. What do you think is going to happen if I state things backwards and take the integral? Like instead of g of x minus f of x, I accidentally do f of x minus g of x. What's that? Like think about 3 minus 2 versus 2 minus 3. Yeah, this is going to give me the opposite answer. Yeah, and so sometimes you might find that you'll set something up, you'll accidentally put things in the wrong order, your number's negative in the end, what the heck? Could be you just switched either the boundaries by mistake or the functions. All right, so cleaning this sucker up, I can distribute this negative right there. So that means this will become a positive 1 over there. So it looks like I have the integral of 2 minus 2x squared. Did I do my algebra okay? 1 minus -1 is 2, negative x squared minus negative x squared. Yeah, it's negative 2x squared. Okay, then we come up with an antiderivative. What's a nice antiderivative here? Antiderivative for 2 is 2x, yeah. So I'm going to have a 2x, Antiderivative for 2x squared, 2/3 x cubed. Yeah, so I got a minus 2/3 x cubed. Don't forget our 2 out front. And our boundaries are 0 to 1. In this case, we love plugging in 0 because that whole side disappears, kind of nice. So this is equal to 2 times. And I'm in the habit of using square brackets before I evaluate and then parentheses or curly brackets after. It's up to you. Helps me keep track of what stage I'm in. So let's see, 2 times 1 is 2, minus 2/3 times 1 cubed, which is just 2/3. And I'll just write it down. Then the technique then would be to go minus parentheses, plug in the next number. Well, 2 times 0 is 0. Minus 2/3 times 0 is still 0. So that part conveniently goes away for me. Let's see, 2 would be the same thing as what? 6/3 minus 2/3 gives me 4/3. Times 2 is 8/3. And I'm generally in the habit of sticking with mixed numbers until the end. Not much more I can do except stay 8. Let's see, 3 goes in there, what, twice with 2 left over. So I could say it's 2 2/3, 2.66666. Let's check. Let's ask GeoGebra what it thinks. Let's see, just looking at the picture, I wonder if we can get a hint if that's right. Well, imagine that if we have a square that's 1 by 1, it's 1 square area. So this is smaller than 1, 2, 3, 4. We get an answer that's smaller than 4. Okay, so reasonable. All right, GeoGebra. I don't think we need this guy anymore. Delete, 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 delete. So we want to see, let's see, x squared minus 1. 1 minus x squared. And then we want to find the integral of g minus f. And I think GeoGebra will understand that. From -1 to 1. Ooh. Oh, okay. Interesting. I wonder if there's a way to get it to shade the right area. And it gets 2.67, which to 2 decimal places is what we have. So I'm going to blow up my font. I'm going to keep using this. Options, font size, I think 28 is pretty good. Yeah. So interestingly, what GeoGebra did here is it recalculated the difference of the functions and said, oh, that's the same thing as 2 minus 2x squared. And this is a graph of what 2 minus 2x squared looks like. So it's showing us the area under that curve, which happens to be the same as the football-shaped area that we wanted. Okay. But it didn't actually draw the picture I was hoping for. I was hoping it would actually shade in between. Oh, I know how to make that happen, but it's a pain in the butt. Yeah. See me Friday. No, there's not. You just have to do the integral in 2 pieces. You'd have to calculate the integral for the top half of the curve from here to 0, and then from 0 to the bottom curve. Okay. So actually, let's do part of that because this is a good question. In the book, hopefully you're reading the book. That is an important part of this class. They say things different than I do. They go over some examples I don't do. Not because I don't think they're important. It's just like I just picked different examples. But please read the book. The book talked about an idea called total area, and I brought it up a couple times in class. Let's look at it right now. Total area is not the same thing as area with integrals. You could say it's the absolute value of the area. Okay. So what I mean by that is just consider these 2 examples we just looked at. This function right here is 1 minus x squared. And we can find, using an integral, the area in there. And this area right here will be positive. On the other hand, those tools keep disappearing. go red, if we consider the graph of x squared minus 1, excuse me. And we find the area in here, guess what that area is going to be if I just do an integral? The integral will say this area is negative, less than 0. Okay. Oops, my 1 is missing there. So that's just an integral finds area. If we just integrated the function x squared minus 1, all of these heights here are negative y values, right? Like this one right here, y is negative 1 there. We're getting a bunch of negative heights added up. It's going to give us a negative area. When we're looking for total area, that means we have to look at the function carefully and say, are there any parts of my function that are underneath the x-axis? Because if I integrate those, they will cancel out with positive stuff. Okay. So, for example, if we were to integrate from, say, negative pi to pi, the sine of x, I don't even have to do any work but visualize the graph. Because if I think about the graph of the sine here, it's got that hump over there and this hump over there. That's negative pi, that's pi. It's an odd symmetric function, which means every point over here has a mirror point down there. This area here is exactly the opposite of that area there. So what do I know this integral must be equal to? It must be 0. Work done. You could go through, find the antiderivative, plug everything in, you'll get 0. Guaranteed. But if I said what I need is the total area of the sine curve in one of its periods, then you would have to find the absolute value of this guy and combine it with that guy to give me what I really want. So that's a slightly different question. So let's do it on this one first, then we'll do it on that one. So what I want now is the total area between y equals 0 and y equals 1 minus x squared on the interval from -1 to 1. Once you see total area pop up, you're thinking, oh, beware of negatives, look at the graph. So then we look at the graph. And we see, oh, this whole thing is negative in that region. So we have two options. We could try and integrate from -1 to 1 the absolute value of our function, 1 minus x squared. Absolute value is a function. Its antiderivative is kind of a pain in the butt. Anybody ever remember seeing a derivative formula for the absolute value of x? Some classes cover it, some don't. The problem with this is the absolute value is two different functions pieced together. It's a piecewise function, right? It's y equals x on this side and y equals -x on this side. Okay. And what that means is if the stuff you're taking the absolute value of is positive, you just leave it alone. You don't have to do anything, right? We saw that earlier. But if the stuff you're taking the absolute value of happens to be negative, this says take the opposite of whatever you have there. So the only way I can get rid of the absolute value here is to realize from -1 to 1, this stuff inside is always negative. How do you make something negative positive? Yeah, you multiply by -1 by taking the opposite. Yeah. So what that means is to get rid of the absolute value, which is a total pain in my butt right now, it complicates life greatly, as simple a function as it is. What I want to do is take the opposite of the integral of, oops, I stated the wrong function up here, didn't I? Why didn't you guys say something? Jesus was thinking, he's like, oh man, you wrote the wrong function up there. What function am I supposed to be graphing? Not 1 minus x squared, but I should be graphing x squared minus 1, yeah. This is a graph of x squared minus 1, x squared minus 1. So to get rid of the absolute value, my only choice is to put a negative out there. If it changed sign multiple times in the integral, we would have to just break the integral up into each part. Negative part, positive part, negative part, positive part. We'll do that for the sign next. All right, so that's what we got to do. So let's try it and see what happens. So when I take an antiderivative, don't forget we have a negative out front of our square bracket. Antiderivative for x squared is x cubed over 3. And then antiderivative for 1, x, evaluated from -1 to 1. We could have used symmetry here and doubled the integral from 0 to 2, but we've gone this far. Let's just keep going. So evaluating this sucker, switch colors, I have the opposite of parentheses. Plugging in 1 gives me a 1/3 minus 1 minus plugging in -1, and -1 cubed is still -1, right? So that's going to give me a -1/3 minus -1, which is really +1. Let's see, what does this give me? Here, that's what, a -2/3? And then this would be then -2/3. -2/3 minus 2/3 is -4/3. But we got this negative chilling out front, waiting to act. So in the end, what do we got? It looks like +4/3. Sorry, I skipped a little arithmetic there. But my belief is this guy right here is a -2/3. And then this guy right here is a +2/3, but I'm subtracting. So I have the opposite of -4/3, which is 4/3. Yeah, I feel good about that. What did we get for our football-shaped area? Anybody remember? I believe it was 8/3. This is the bottom half of that 8/3, so 4/3 makes sense. Yeah, that's the area in the bottom half. Okay. And we got a positive answer because we knew how to adjust it. Okay, total area means beware of the sign of the function. So let's do it again, total area. So let's get the total area of the sine of x on the interval from, let's see, 1 period. We could go like from -pi to pi or 0 to 2 pi. Sounds like more fun. Clint, what do you think? Too slow. Ventura. That's okay. -pi to pi or 0 to 2 pi? 0 to 2 pi. Excellent choice. Okay. I want the total area of the sine over 1 period. Right? So we just have to pick an interval that covers 1 period. So anytime total area pops up, really anytime area pops up, make a graph by hand or on the computer. Sine, I remember, starts at the origin and then it starts to wiggle. There's 1 period. I know a period is 2 pi long. Given the symmetry of the sine, I know that pi appears exactly in the middle. I know it peaks at 1 and bottoms out at -1. And so here I desire to know what these two areas are in absolute value. If I just integrate straight from 0 to 2 pi, what's going to happen? I get 0. Yeah, that's boring. So let's see. There's a couple of different options here. One option would be to say, all right, the first part from 0 to pi, that's wicked easy. Oops, that's not a pen. I would just integrate from 0 to pi the sine of x dx. Now the next part I know is going to be all negative area, so I can just compensate by just putting a minus in front and then integrating from pi to 2 pi. Sine of x dx. Now, that's the general approach you would take. You look at the function. Where is it positive? Okay, take the integral of the positive part. Where is it negative? Take the opposite of the integral of the negative part. But here we have a shortcut. It's easier than that here. What other feature of the sign can I use to make this easier? Yeah, this down here is really just a mirror image of that up there. They have the same area. So really, I just need 2 times that guy right there. I don't even need to do the other part separate. We're going to do it both ways just to make sure it works out. You could take my word for it and hope I'm not a liar, or you could just do it and see what happens. Well, let's do it. What's the antiderivative of sine? Negative cosine. Yeah, we got to be careful about those. Those are kind of tricky. When I'm playing around with antiderivatives, I will often have a list of derivatives nearby. I think I put one here. There it is. Derivative formulas on the resource page. You got, yeah, you have, yeah. So I have those out, right? You're always going to be referring back to those. And as we progress through the course, we're going to develop a table of integrals. And actually, who's got their print book with them? Anybody? Oh, Ventura does. I think at the end of your book, there's pages and pages of integral formulas to go with the derivative formulas somewhere. Oh yeah, yeah. Look at that formula 156. Yeah, we'll worry about those guys later. Yeah. So the book has integral formulas in the back. There will be a test that'll allow you to scan through those, but most tests, I need you to show me you know how the formulas work without, it's not cheating. Oh, good question. Can you bring the derivative formulas on the test? I will provide them. How about that? I will provide this page of derivative formulas on the test. Just because some people are taking this online and I want everyone to have the same tools, so I'll provide the sheet. That'll be easier. Yeah, I'll provide this page with the test. Sure. Okay, where were we? Anyway, so every once in a while, it's a good thing to refer back just to make sure you got it right. So negative cosine is the antiderivative. So evaluating for the first part, I have the negative cosine of x evaluated from 0 to pi minus the negative cosine of x evaluated from pi to 2 pi. All right, so let's see. Cosine of pi is -1. So I have the opposite of -1. Sometimes if this were on a test, I'm doing a bunch in my head. That's really bad. I should actually write down negative cosine of pi minus the negative cosine of 0. Look at all these negatives floating around, right? Danger, danger, danger. That's just the first part here. Cosine of pi is -1. I want the opposite of that, which is 1. Here I have the opposite of a negative, or subtracting a negative, which is plus. Cosine of 0 is 1. 1 plus 1 is 2. So I just found the area of the first hump is 2. Okay. We're going to double check that the next hump has the same one. So here I have minus, and instead of this bracket, I'm going to use a curly bracket. I've got the opposite of the cosine of 2 pi minus parentheses the opposite of the cosine of pi. Lots of brackets. Okay, let's see. Cosine of 2 pi is the same as cosine of 0, right? So I'm going to have a minus -1. Here I have minus, minus. So those guys give me a plus, and then the cosine of pi is -1. So I am subtracting a -2, which fortunately is the same thing as adding a 2. So yeah, we got a total area of 0. So when I'm doing my homework, I try to do those things in my head just to exercise my brain. On a test, that is suicide. Don't do it no matter how good you think you are. Write it down, right? Look at this. Negative, negative, negative. Too much to keep track of in your head. Write it down, frees your brain to think more clearly. All right, we're almost out of time. Darn, we're out of time. Okay, so that's it for today. We have actually started section 5.6. 5.6 is using substitutions to deal with situations where you have area under a curve. Okay, which means we have to evaluate pictures of functions. We have to decide what endpoints to play with. So at the moment, we're still on track for a test on Thursday. There is a 45% chance that I will move the test to Monday. So we'll see. So jump into your homework, and then we'll... Where do you live? Oregon. Okay. Yeah, that's a trek, right? Yeah. We could probably find you a place to take the test in Oregon. There's a library, isn't there? Yeah. Call the librarian and say, hey, your mom's a librarian. That complicates matters. All right. Anyway, so have fun with the homework.